Problem 1. Sketch a graph of a function that satisfies the following. Okay, so we're going to draw a graph here. The limit as x approaches 0 from the left of f of x is 4. So as the function is getting close to 0, the left-hand side, as we approach 0 from the right, we want to approach a y value of -1. And f of 0 itself is 3. The limit as x approaches 3 from the right is 5. And f of 3 is -3. Okay, that's all the information, and now we can just fill in the rest as a nice continuous function. All right, so it does have these breaks. You have to have a break here at 3, okay? Or at least a hole in the graph and a point down. And there's definitely a break here at 0. There's no way to make the function not have a break. One of the key things to remember is that the graph is a function. It needs to pass the vertical line test, so no pieces above each other. Problem 2. Evaluate the limit as x approaches 2. Root 9x plus 7 minus 5 over x minus 2. If we try direct substitution, I can see that I'm going to get a 0 in the denominator. Okay, if we put in 2, 9 times 2 is 18, plus 7 is 25, square root of 25 is 5, so 5 minus 5 will get a 0 on the top also. Okay, so then what we can do instead is try to rationalize the numerator. So I'm going to multiply by the square root of 9x plus 7 plus 5 on top and bottom. So I'm going to have the limit as x approaches 2. When I multiply out the numerator, we'll have the 9x plus 7. Then 5 times the root minus 5 times the root, those add to 0. And -5 times +5 is minus 25. In the denominator, this x minus 2 term I'm going to leave factored out. Okay, so essentially I'm going to do nothing in the denominator. Okay, so let's keep simplifying the numerator. 7 minus 25 is -18. Everything else we just copy down. Okay, now in the numerator I can factor out a 9. So we have 9 times x minus 2. And what we're going to do is, what we can do now is cancel these x minus 2 terms. Now that I've canceled that x minus 2, I can actually do direct substitution. And we'll have 9 over, when I plug in 2, 18 plus 7 is root 25. So I'll get 9/10. Okay. Problem 3. Give a function, a formula, not a graph, that is discontinuous at x equals 2, but continuous everywhere else. Okay. So look at a couple of different ways to do this. One way is I want something where it's not continuous at x equals 2, and maybe I can do that by having it not defined at x equals 2. So I'll put in x minus 2 in the denominator. Okay, and then anything we want in the numerator. So this function is undefined at x equals 2, and therefore not continuous there. Okay. But since it's a rational function with domain x not equal to, it's continuous everywhere else. Okay. Another example of a function would be a piecewise function. So if I have something like x plus 4, if x is less than or equal to 2, and we have 5 minus x, if x is greater than 2, then the limit as x approaches 2 from the left. Okay, as we approach 2 from the left, we'll be using the function, the formula x plus 4 for the function. And so then, using direct substitution, I get that the limit is 6. However, if I look at the limit as x approaches 2 from the right, then we use the formula 5 minus x. So I'll have 5 minus 2, or 3. Since these don't match, the limit doesn't exist. So g of x is not continuous. So g of x is not continuous at x equals 2. However, g, because it is a polynomial for all of the x's, g is continuous everywhere else. Okay, moving on to problem 4. We're sketching a graph. To sketch a graph of a function where the domain is everything except 5. So at 5, I want it to be undefined, so maybe I'll have a hole in the graph. Okay, it does have to be defined everywhere else, so I have to be a little bit careful. It's continuous everywhere except at 1 and at 5. Well, it's not defined at 5, so it's not going to be continuous there. I also want it to not be continuous at x equals 1. So I could maybe have a hole in the graph. Or, I'm sorry, can't have just a hole in the graph because it has to be defined. So I can have maybe like a jump in the graph. Okay. And at -3, it has to be defined and continuous, but not differentiable. Okay. So one way that I could do this would be to have at x equals 3, a vertical asymptote. One way that I could do this is at x equals -3, I have a vertical tangent line. Okay, so here the vertical tangent makes the derivative not defined, but the function is continuous. At 1, I have a jump in the graph, so it's continuous, but it is still defined. And at 5, there's a hole in the graph, so it's not defined. Another way that we can do this is to show you other options that we have for each of these values. Instead of a hole in the graph, I could have also had a vertical tangent line, a vertical asymptote. Okay. At x equals 1, it needs to be defined, so I could have instead of a jump, I could just have a hole in the graph filled in at another point. Okay, and at x equals -3, I want it to not be differentiable. Another way to do that would be with a cusp or sharp corner. Okay, so this is just giving you different set of options so you can see how to graph things that are continuous or differentiable at different points. Moving on to problem 5. Find the derivative using the limit definition. Okay, so f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. So let's write down what this looks like. F of x is x plus 2 over x minus 1. So f of x plus h is x plus h plus 2 over x plus h minus 1. And there's no simplifying that I can do here. There's nothing to multiply out or anything like that. So I'm going to go ahead and just plug in these pieces. So we have x plus h plus 2 over x plus h minus 1 minus x plus 2 over x minus 1. All of this is divided by h. Okay. So in order to be able to make some progress here, I'm going to try to combine these two fractions together in the numerator. So I'm going to get a common denominator. The fraction on the right, I'm going to multiply by x plus h minus 1, top and bottom, so that it has that factor in the denominator. The fraction on the left, I need a factor of x minus 1. So multiply by x minus 1 on top and bottom. Okay. Now, instead of dividing by h, I always think of this as like an h over 1. I can instead flip that. Dividing by a fraction is the same as multiplying by the reciprocal. So I can write this as like a 1 over h instead. Okay, and I have a common denominator now. So we have this x minus 1 times x plus h minus 1 in the denominator. Okay. All right, so in the numerator, we have x minus 1 times x plus h plus 2 minus x plus 2, x plus h minus 1. Right? And so now what I want to do is simplify the numerator as much as possible. So we're going to start by FOILing out everything. So I'm going to distribute this x. So x squared plus xh plus 2x. Distribute the -1. It's x minus h minus 2. Okay. For the subtraction, I think that it would be easier if I start by distributing this negative. It doesn't distribute twice, right? When we're multiplying numbers, I don't multiply them over and over again. So this negative I can think of as a -1, and I can multiply it into here, and that's it. So now I'm going to distribute this negative x. So I have minus x squared minus xh plus x. And now I'm going to distribute this -2. So I have minus 2x minus 2h plus 2. Don't do anything in the denominator because I don't have any good reason to. Okay, let's find things that add to 0. So x squared minus x squared add to 0, xh minus xh add to 0, 2x minus 2x, minus x plus x, minus 2 plus 2. And the only thing I have left is a minus h minus 2h. So combining those, I'm going to get a minus 3h. So now this factor of h that I have in the numerator, this factor of h in the denominator can cancel. So let's rewrite. We have the limit as h approaches 0 of -3 over x minus 1, x plus h minus 1. And now I do direct substitution. And I have an x minus 1 times x minus 1 in the denominator. So that's an x minus 1 squared. Okay, problem 6, let's do some derivatives. For f of x equals e to the x times the square root of x times tangent x, find the derivative. I'm going to start by rewriting this problem where the root is instead written as a half power. Okay, and I can see that I have a product of two functions. So when I go to find the derivative, I'm going to use the product rule. So we have the derivative of the first times the second left alone plus the first times the derivative of that second piece. Okay, so now let's work out these derivatives. Derivative of e to the x, it's just e to the x. Okay, and now for this derivative, I have stuff inside a half power, so I'm going to use the chain rule. So the 1/2 comes down, inside stays the same, lower the power by 1, and multiply by the derivative of the inside stuff. Okay, so now let's recopy. Now, this thing I'm differentiating here is a product. So in parentheses, I'm going to do the product rule. So I have the derivative of the first, derivative of x is 1, times tangent x left alone, plus the first x left alone, times the derivative of tangent x, which is secant squared x. Okay. Problem 7, find the derivative of this quotient. So I'm going to use the quotient rule. So we have the derivative of the top times the bottom left alone minus top left alone times the derivative of the bottom all over the bottom squared. Okay, now let's work out these derivatives. The derivative of x e to the 5x, I have two multiplied pieces, so this is going to be a product rule. So we have the derivative of x, which is 1, times e to the 5x, plus x left alone, times the derivative of e to the 5x. Okay. The derivative of e to the 5x, that's a chain rule. Outside function is e to stuff, so I'm going to get e to that same stuff times the derivative of the inside stuff. The derivative of 5x is 5. Okay, so I have e to the 5x times 5. Okay, so that was that derivative that I had. And then times 9 minus x squared. And then when I go to differentiate 9 minus x squared, the derivative of 9 is 0, and the derivative of negative x squared is minus 2x. And that's it. Problem 8. Find an equation of the tangent line to y equals 3x squared plus 10x minus 2 that is parallel to 2y minus 8x equals 4. So parallel to means the same slope, so let's find the slope here. So 2y equals 8x plus 4. So y is 4x plus 2. So here the slope is 4. So I want to find a tangent line that has slope 4. Okay, I know that if I differentiate the function, so I'll call this f of x. Okay, if I differentiate the function, the derivative outputs slopes. So f prime of x is 6x plus 10. So then we want to solve prime of x equals 4. So 6x plus 10 equals 4. So 6x is negative 6. So x is negative 1. So now I have an x value. I can plug into the function to get a y value. So I have 3 times negative 1 squared plus 10 times negative 1 minus 2. Okay, so 3 minus 10 minus 2 is negative 9. So we have a y value of negative 9. Okay, so we put this together to our point slope form of a line. So y minus negative 9 equals 4 times, oh, that should have been x minus x1. So x minus negative 1. Okay, so y plus 9 equals 4 times x plus 1. Distribute the 4. And then subtract 9. So I get y equals 4x minus 5. Okay, problem 9. Let's do some limits. First one, limit as x approaches 1 of ln of x over sine of pi x. All right, let's try direct substitution. If I plug in a 1, ln of 1 is 0. Sine of pi is 0. So we have a 0 over 0. So we can use L'Hopital's rule. So I'm going to get the limit as x approaches 1. Take the derivative of the numerator, 1 over x. Derivative of the denominator, cosine of pi x times pi. Chain rule. Okay, and now let's try direct substitution. When I plug in 1 in the numerator, I get 1 over 1. In the denominator, we'll have cosine of pi times pi. And cosine of pi is negative 1. So I have negative 1 over pi. Okay. Next up, we have the limit as x approaches infinity of e to the 2x all over x squared. I try direct substitution. E to the infinity is infinity. Infinity squared is infinity. We have infinity over infinity. So we have the right form for L'Hopital's rule. So I have new limit as x approaches infinity. I differentiate the top, I have e to the 2x times 2. Differentiate the bottom, and I get 2x. And this is still an infinity over infinity. So we do L'Hopital's rule again. So I have the 2 hangs out. The derivative of e to the 2x is e to the 2x times 2. I have that extra factor of 2, so I'll have e to the 2x times 4. In the denominator, the derivative of 2x is 2. And now, when I try direct substitution, I'm going to get infinity over 2, which is infinity. So the limit as x approaches infinity, e to the 2x over x squared is infinity. All right. Next up, we have the limit as x approaches negative infinity, e to the 3x over x cubed. And this one looks very similar to part B. It's the approaching negative infinity that makes a difference. Okay. I look at a graph of e to the x. As x goes off to infinity, the y values go up to infinity. But as my x values go to negative infinity, the y values go to 0. So when we try direct substitution, we get 0 over infinity. And numerator is pulling me towards 0. A 1 over infinity is also pulling me towards 0. So this limit is just 0. Okay. Next up, we have the limit as x approaches 0 from the right of x times ln of x. This one is not a fraction, so it's definitely not going to be the right form for L'Hopital's rule. So right away at the beginning, I'm going to take that x and force it into the denominator as an x to the negative 1 power. Okay, now let's try direct substitution. In the numerator, what I'm going to do is recall the graph of ln of x looks like. Okay, as my x values go towards 0, the y values go down to negative infinity. And for a 1 over x, as x goes to 0, I'm going to go to infinity, so I have an infinity over infinity situation, so we have the right form for L'Hopital's rule. So the derivative of ln of x is 1 over x. The derivative of x to the negative 1 is negative x to the negative 2. Okay, and now I'm going to simplify. So this x to the negative 2 I can bring into the numerator as an x to the positive 2. Okay, so my negative is hanging around. And x squared over x can simplify a little bit. So we have the limit as x approaches 0 from the right of negative x, and direct substitution will just give us 0. Summarizing, the limit as x approaches 0 of x times ln of x is 0. All right. Next up, we have the limit as x approaches 0 of tangent x minus x over x cubed. If I try direct substitution, I get tangent of 0, which is 0. Okay, 0 minus 0 is 0 over 0 cubed, right? At the 0 over 0 situation, so we use L'Hopital's rule. Okay, so the derivative of tangent x is secant squared x. The derivative of x is 1. And in the denominator, the derivative of x cubed is 3x squared. Okay, so now I try direct substitution. Okay, secant is 1 over cosine, right? Cosine of 0 is 1. Reciprocal is still 1. Squared is still 1. So I get 1 minus 1 on top, and I get and then in the bottom I get 3 times 0 squared. So we have 0 over 0 again. Let's do L'Hopital's rule again. Okay, so on the bottom we'll have 6x. The top for secant squared, secant x is the inside function and stuff squared is the outside. So I have 2 times secant x to the power of 1 times the derivative of secant x, and the derivative of secant x is secant x times tangent x. Okay. And if I try direct substitution, tangent of 0 is 0. So the whole numerator is all multiplied stuff, so that's all going to be 0. So we have 0 over 0. We're going to have to do L'Hopital's rule again. Before we do that, I'm going to simplify this down a little bit. So I'll write this as 2 secant squared x times tangent x all over 6x. Now, you can get away without doing a L'Hopital's rule here. If you break tangent into sine over cosine, the sine x over x as x goes to 0 is one of our special limits that maybe some of you remember, so you could break that off and evaluate it, and the whole thing will come out quite nicely. If you don't remember that, though, and I think that's probably most of you wouldn't make that observation, we're just going to do a L'Hopital's rule here. Okay, so it's more work, but I think that it's something that more of you would see to do. So we have a product of two things. In the numerator. So we have the derivative of the first. So this 2 out front. We already looked at the derivative of secant squared x, right? We said that that was secant x times tangent x. Okay, so that's the derivative of the first times the second plus first left alone, 2 secant squared x. Times the derivative of the second. The derivative of tangent x is secant squared x. The derivative of 6x is 6. And now when I do direct substitution, remember when I plug in 0, cosine of 0 is 0. Sorry, cosine of 0 is 1. Secant is 1 over that. 1 over 1 is 1. So we're going to get 2 times 1 times 1 times 0 times 0 plus 2 times 1 squared times 1 squared all over 6. Okay, so I have 0 plus 2 over 6, or 1/3. So the limit as x approaches 0 of tangent x minus x over x cubed is 1/3. All right. One more. We want the limit as theta goes to 0 of sine of theta minus sine theta cosine theta all over theta squared. And once again, if you remember your trig limits, the sine and cosine one, this can be a very quick and easy problem. If you use L'Hopital's rule, it takes a little bit more effort, but you can still get there. Okay, so I'm going to try direct substitution. Okay, so sine of 0 is 0, so I have 0 minus 0 over 0 squared, right? 0 over 0, that's the right form for L'Hopital's rule. So I'm going to go ahead and differentiate the top and bottom. The derivative of sine theta is cosine theta. And then here I'm going to have a product rule. What I'm going to do, instead of thinking of this as minus stuff, I'm going to think of it as plus, and the first one is a negative sine theta. So when I take the derivative of negative sine theta, I'll have negative cosine theta times cosine theta plus the negative sine theta times the derivative of cosine theta, which is negative sine theta. And in the denominator, the derivative of theta squared is 2 theta. Okay, so now we have the limit as theta goes to 0, cosine theta. Here I have cosine times cosine, that's cosine squared, sine times sine is sine squared, but one of them is negative and one of them is positive. So I have minus cosine squared theta plus sine squared theta. Okay, so if I try direct substitution, okay, when I plug into cosine, plugging in 0 is going to give me 1. So we have 1 minus 1 plus 0 over 0. That's 0 over 0. Okay, so we do L'Hopital's rule again. Okay, in the denominator, I'm going to get just a 2, so I know there's no more L'Hopital's rule after this. The derivative of cosine theta is negative sine theta. Here I have minus, the 2 comes down, the inside stuff is cosine theta. The derivative of cosine theta is negative sine theta. For sine squared theta, the 2 comes down, the inside is sine theta. The derivative of the inside stuff is cosine theta. Okay, and now when I plug in, I'm going to have a 0, 0, 0 on top over 2. So the whole limit is just 0. Oops, I wrote x. Okay. Right, problem 10. A 6-meter ladder is leaning against a wall. Let's go ahead and draw the situation. So a wall, we have a ground, and then we have a ladder leaning up against the wall. Okay, the top of the ladder is slipping down, and the bottom of the ladder is sliding away from the wall. Okay, so what I'm going to do is I'm going to label some distances. I'm going to label x as my distance between the wall and the bottom of the ladder. And I'm going to label y as the distance between the ground and the top of the ladder. So if the ladder is slipping down the wall at a rate of 1.5 meters per second, then dy dt is negative 1.5. Okay, and how fast will the bottom of the ladder be moving away? My goal is to find the x dt when the top of the ladder, so y, is 4 meters above the ground. So when y equals 4. Okay. The ladder is 6 meters long, and it doesn't look like in this problem it's changing at all. So that distance is 6 meters. And so if I want to find an equation that relates my variables, I'll use the Pythagorean theorem. X squared plus y squared equals 6 squared. Okay, so now we we have information about the derivative of y. We want to know about the derivative of x. So these variables are all good. We go ahead and differentiate. My variable here is time. Things are changing over time. So each of these are functions of times. We're using implicit differentiation. So the derivative of x squared is 2 times x times dx dt. The derivative of y is 2y dy dt. And 6 and 6 squared, right? Those are constants. The derivative is 0. Okay, so I want to find dx dt, so we'll subtract. So 2x dx dt equals negative 2y dy dt, and then divide. Dx dt is negative 2y dy dt all over 2x. And the 2's cancel. So I need to know dy dt, which I have. I need to know y, which I have. And I need to know x, which I don't have. So we need to find x when y is equal to 4. So I'll go back to my original equation. X squared plus 4 squared equals 6 squared. So x squared plus 16 equals 36. We subtract. So x squared is 20. So x is the square root of 20. We could write a positive and negative here, but I don't want a negative value for x because it's a distance. Okay, so dx dt is going to be negative 4 times negative 1.5 all root 20. So my negatives will cancel. 4 times 1.5 is 6. So I get 6 over root 20 meters per second. You can mess around with that rationalizing and things, but I think once we get down to a number, we can stop. Problem 11. A cistern is used to catch rainwater and has the shape of a cone. Okay. So here's my cone-shaped cistern. It's collecting rainwater. Okay. Remember, I want to model the water inside. So the water inside is going to have a radius r and a height h. The container says it's 2 meters deep. And the diameter at the top is 3 times the depth. So the diameter, if the whole cistern is 2 meters deep, then the diameter is going to be 3 times that, so that's 6 meters, which leaves me with a radius of 3. Okay, so there's 2 ways to do this. We can use this relationship that they gave us. The diameter is 3 times the depth, so diameter is 3h, or twice the radius is 3h. So the radius is 3/2 h. Or another way to go about this would be to make similar. Another way to get to the same conclusion is just to make some similar triangles. So on my container, I have this triangle where height is 2, top 3, it's a radius, and then inside the water, we have r and h. So setting this up, r over h is equal to 3 over 2. Okay, and I can get the same relationship. All right. On a rainy day, water is collecting at a rate of 20 liters per minute, or 0.02 meters cubed per minute. So dB dt is 0.02. but being drained out the bottom at the same time. Okay, so maybe I shouldn't write that as dV dt, because now I'm saying, wait a minute, there's other stuff going on. Let's just write this as water in. If the depth of the water is increasing, okay, so that's telling me a rate of change of height. It's increasing at a rate of 0.001 meters per minute when the water level is 1.5 meters deep. Find the rate at which water is draining out the bottom. So I want to find out how fast the water is going out. Okay, so dV dt, the rate of change of volume, that's going to be water in minus the water out. Okay. And I know that the water in is 0.02. So dV dt, crazy. So dV dt is 0.02 minus the water out. So doing a little algebra, water out is 0.02 minus dV dt. So if I can find dV dt, then I'll have the answer to my question. Okay. All right, so then what I can do is say, well, this is a cone. I have a relationship between volume and radius and height. Volume is 1/3 pi r squared h. And I'm told dH dt. I want to find dV dt. I want to get rid of r. I'll use my relationship. R is 3/2 h. Okay, so I replaced the r with a 3/2 h, and now I'm going to simplify. So 3/2 squared will give me a 9/4. H squared times h gives me an h cubed. Okay, so now we can differentiate. So I get dV dt equals 1/3 pi times 9/4 times 3h squared dH dt. Okay. The 1/3 and the 3 cancel. I want to find dV dt. I have a value for dH dt and h, so I can just plug in as it is. So I get pi times 9/4 times 1.5 squared times 0.001. I think for this one, we'll just plug this in our calculator and get a decimal approximation. Okay, so this works out to 0.0159. Okay, that's dV dt, so I can plug that in here. So the water out is 0.02 minus 0.0159. I get 0.0041. Okay, that's it. Problem 12. A Norman window has the shape of a rectangular surmounted by a semicircle. So I have a rectangle with a semicircle on top. So the diameter of the semicircle is equal to the width of the rectangle. Okay. So let's go ahead and label some variables. Right, on the circle, radius r, and then on the rectangle, we'll say we have a width maybe I'll call it x, and the length y. Okay, so I know that 2r equals x. That was that thing given here. If the perimeter of the window is 80 feet, find the dimensions of the window so that the greatest possible amount of light is admitted. So we want to maximize the area of the window. That's our goal. Okay, so let's start with a formula for area. The area is going to be the area of the rectangle plus the area of the semicircle. Okay, the rectangle, the area is x times y, right? Length times width. Semicircle is 1/2 of a circle, so we have 1/2 times pi r squared. Okay, so we're doing pretty good. We have a formula now for area. This is a function of 3 variables, x, y, and r. So we need to eliminate some variables, and we have some help with that. We said at the beginning here that 2r equals x, so I can replace my x with a 2r. All right, so that's one variable gone. I still have y and r in my function, so we need to get rid of one of these. So let's go back to this other piece of information. The perimeter of the window is 80 feet. So what I'm going to do is I'm going to start at one corner, and I'm going to figure out the perimeter, right? So going over, I get x. And going up, I get a y. Going around the outside, I get 1/2 of a circle. So I have 1/2 of circumference, which is 2 pi r. And then coming back down, I have another y. So that's the distance around, and we said that is 80 feet. So x plus 2y plus pi r equals 80. And we already know that x is 2r. So 2r plus 2y plus pi r equals 80. Let's go ahead and solve for y. I think that's going to be a little bit easier than solving for r. So to get 2y by itself, we subtract. So 2y is 80 minus 2r minus pi r. And then let's divide both sides by 2. So y is 40 minus r minus pi over 2r. Okay, looks good. Let's plug that in for y. So area is 2r times 40 minus r minus pi over 2r plus 1/2 pi r squared. Okay, let's simplify a little bit. Distribute this 2r, so I have 80r minus 2r squared minus pi r squared plus 1/2 of pi r squared. So a negative pi r squared plus 1/2 of pi r squared is going to give me a negative 1/2 pi r squared. Okay, so now we have area is just as a function of just one variable r, and we've simplified this as much as possible. So now let's differentiate. So a prime is going to be 80 minus 4r minus pi over 2 times 2r. The 2's cancel here. And what I want to do is figure out where a prime is equal to 0 or where a prime is undefined. Okay, but this is a polynomial, so there's no solution where it's undefined. Okay, so we have 80 minus 4r minus pi r equals 0. So let's get the r's on one side and everything else to the other. So negative 4r minus pi r equals negative 80. Factor out the r. So I'm left with r times negative 4 minus pi. And then we divide. So r is negative 80 over negative 4 minus pi. Or I can write that as 80 over 4 plus pi. Okay, there's nothing wrong with just going to decimals for this, although dimensions are kind of nice if you leave them as these weird fractions. Okay, but as a decimal, that comes out to 11.2 and change. Okay. It says find the dimensions, so once I have r, I need to go back and find both x and y. Okay. So x is going to be double that. So I get 22.404. And then y, if I plug into this, I actually get the exact same number again as r. Okay, and again, you can just leave them as decimals, but if you leave them as fractions, you can see that it is indeed exactly the same number. Okay, so those are the dimensions that will maximize the amount of light coming in the window. Problem 13, a metal can is to be constructed with a volume of 100 cubic inches. The can is a right circular cylinder, so let's go ahead and draw that. Okay, so I have height h, and we have a radius r. All right, if the cost for the metal size of the can is 4 cents per square inch and the cost of the top and the bottom is 5 cents per square inch, find the cost of the cheapest such can. So we want to build a function for cost, and then we want to minimize that. So our cost, I'll just write that as C, is going to be the cost of the top plus the cost of the bottom plus the cost of the sides. Okay, the top of the can is 5 cents per square inch, and the area, since it's a circle, is pi r squared, so 5 times pi r squared. The bottom is the same thing, 5 times pi r squared. And for the side, if we were to unroll it, we would have a rectangle with height h, and width would be the circumference of the circle. So we have 4 cents times the height times the circumference, 2 pi r. Okay, so simplifying, I'm going to get 10 pi r squared plus 8 pi r h. We have two variables here, r and h. So we need to eliminate a variable. We're told that the volume is 100 cubic inches, so that's our constraint. So volume of a cylinder is pi r squared h, and that's equal to 100. Okay, so if I want to eliminate a variable, it will be easier to get rid of the h, so I'll divide. 100 divided by pi r squared is equal to h, so I'll plug that in for h. So we have 10 pi r squared plus 8 pi r times 100 over pi r squared. And let's simplify a little bit. Pi's cancel. One of the r's cancels. So we get 10 pi r squared plus 800. And I'm dividing by r. I'll write that as an r to the negative 1. So now we have cost as a function of just one variable. So we differentiate. This is a regular derivative. So 2 comes down, we have 20 pi r minus 800 r to the negative 2. I like to write that so I don't have the negative exponent. So we could write this as 800 over r squared. Okay, so now we need to find out where is the derivative of 0 and where is the derivative undefined. Okay, it's going to be undefined when r is 0, but then I don't have a can, so that doesn't make any sense. Okay, so if I want to figure out where this derivative is 0, we have 20 pi r minus 800 over r squared equals 0. I'm going to multiply everything on both sides. pi r squared to get rid of my fractions. So we have 20 pi r cubed minus 800 equals 0. So 20 pi r cubed equals 800. Divide both sides by 20. So on the left we get pi r cubed. 800 divided by 20 is going to be 40. So r cubed is 40 over pi. So r equals the cubed root of 40 divided by pi. Be a decimal for that. .3351. All right. The instruction said find the cost of the cheapest such can. So once I have that r value, the only critical point, so it's got to be the minimum, what I can do is I can plug that back into my cost function to get the cheapest cost. Okay, so we have 10 times pi times 2.3351 squared plus 800 divided by 2.3351, and I get 513.8991. This is cents, or $5.14 if I round to the nearest penny. Okay. Problem 14. G of x is secant of arctangent of x. Find the derivative. Okay, so there's two ways to do this problem. I'm going to start this with what I think is the most straightforward way, and then afterwards I'll show you a shortcut if you're really good with your trig stuff. Okay, so the straightforward way is just to start differentiating right away. Okay, so we have a chain rule. My outside function is secant. The derivative of secant x is secant x times tangent x, but the chain rule says don't plug in the x, plug in the inside function. So I have secant of arctangent x times tangent of arctangent x times the derivative of arctangent x, which will give me secant of arctangent x times tangent of arctangent x, and the derivative of arctangent x is 1 over 1 plus x squared. You won't have to have that memorized for the exam. Okay, so we could just call it there. We could say we're done. All right, but this simplifies a bit, right? For example, tangent of arctangent of x, that should simplify down to just x. Okay, maybe something funny happens over here too. So another way to go about this is to say, well, what happens if I take this g of x, secant of arctangent x, and see if I can simplify it or rewrite it in some way first. Okay, so typically I think of inputting an angle into a trig function. Okay, so it inputs an angle and outputs a number. So the inverse function will go the opposite way. It would input a number and output an angle. So let's just let the angle theta be arctangent of x. So then tangent theta would be x. And so if I draw a right triangle with an angle of theta, and I know that tangent of theta is x, well, tangent theta is opposite over adjacent, so I'll make that an x and that a 1. Okay, so using the Pythagorean theorem, 1 squared plus x squared equals this side squared. So this side is the square root of 1 plus x squared. Okay, so my g of x is secant of arctangent of x, which is secant of theta. Secant of theta is hypotenuse over adjacent. So this is just the square root of 1 plus x squared. Okay, so another way to do this problem is to say, oh, if g of x is secant of arctangent of x, then it's really just the square root of 1 plus x squared. So then g prime of x is 1/2 1 plus x squared to the negative half times 2x, or x over the square root of 1 plus x squared. Okay, so this is another perfectly viable solution to this problem. And if we did a bunch of simplifying over here, we would get to that spot. Okay. Problem 15. H of x is the sign raised to the power of natural log of x. So we want to find the derivative of this thing, but we don't have a derivative rule for these powers, so we're going to get rid of the powers. So let's start with a log. Natural log of h of x equals natural log of sine x to the power of ln of x. So now we can bring this ln of x down out front. So ln of h of x equals ln of x times ln of sine x. And now we differentiate. Okay, on the left, the derivative of ln of h of x is 1 over h of x times h prime of x. On the right, I have a product rule. So we have the derivative of the first times the second left alone plus the first left alone times the derivative of the second. Okay, so now let's work out what those derivatives are. The derivative of ln of x is 1 over x. The derivative of ln of sine x, I'm going to use the chain rule. I have 1 over the inside stuff times the derivative of the inside stuff. So we get cosine x over sine x. And in order to solve for h prime, I need to multiply both sides by h of x. Okay. So h prime of x is going to equal h of x times all of the stuff. But instead of writing it as h of x, I'm going to write my formula that we had originally. Sine x to the power of ln of x. Okay, so you could write cosine x over sine x as cotangent x if you like, or not. Either way is fine. All right, problem 16. Find the absolute max and absolute min of f of x equals natural log of 2x over x on the interval 1 to e. So first we're going to find the critical points. So I'm going to find f prime of x. We have a quotient, so I'm going to use the quotient rule. So we have the derivative of ln of 2x times x left alone minus ln of 2x by itself times the derivative of x all over x squared. Okay, the derivative of ln of 2x is going to be 1 over 2x times the derivative of the inside stuff, which is 2. The derivative of x over here is 1. Okay, so simplifying, 2 over 2 cancel, x over x cancel, so I get 1 minus ln of 2x in the numerator, x squared in the denominator. Okay, so let's solve for where f prime is equal to 0, and also where f prime is undefined. So it's going to be equal to 0 where this numerator is 0. So 1 minus ln of 2x equals 0. So 1 equals ln of 2x. Take e to the power of both sides. So e equals 2x. So e over 2 equals x. Figure out where f prime is undefined. That's where the denominator is 0. So I get just x equals 0. to find absolute max and min, what I'm going to do is I'm going to take my critical points and endpoints, and I'm going to test them into the function. Okay, this is on the interval 1 to e, so I only want things that are in between 1 and e. Okay, e over 2 is in between 1 and e, but 0 is not, so it doesn't get on this list. Okay, so now we go ahead and plug in here. When I plug in 1, I'm going to get just ln of 2. And I think that for all of these, it's beneficial to get a decimal approximation. So I get 0.6931. Okay. When I plug e over 2 in here, we'll stick with the decimal approximations, right? I'll get 0.7358. And when I plug e in, I get 0.6229. So the biggest one of these is the 0.7538. That's the max. The smallest one is the min. All right. Question 17. Find dy dx by implicit differentiation. All right. So there's no real simplifying to do here. I'm going to just jump right into a derivative. For the e to the x over y, e to the stuff is my outside function, so we're going to start with the chain rule. So I get e to that same stuff times the derivative of the inside stuff. Okay. I can write this as x to the half and y to the half. So I'm using the power rule here, so I get 1/2 x to the negative half. Differentiate y to the half, I get 1/2 y to the negative half times the derivative of the inside stuff, so times dy dx. Okay, so now let's go back and finish off our derivative of x over y. So I'm going to use the quotient rule. We have the derivative of the top, which is 1, times the bottom, minus the top, times the derivative of the bottom. The derivative of y is dy dx, of the bottom squared. And the right-hand side, I'm just recopying down all of the derivative work that we already did. Okay, we need to solve for dy dx. So what I'm going to do is I'm going to take this e to the x over y and distribute it. And I'm going to do the same thing with the y squared. I'm going to kind of break that up into a fraction. Break the one fraction into 2. So we have e to the x over y times 1y, so I'll just write times y over y squared, minus, I have y squared, we have e to the x over y, and then the dy dx. Okay, the right-hand side I'm not really doing anything with yet. What I want to do is get everything with dy dx on one side and everything else on the other. So what I'm going to do is just add to get this big term over here, and subtract to get the 1/2 x to the negative half on the other side. Okay. Maybe a little bit of simplifying as we go, cancel those y's. So I have 1 over y e to the x over y minus 1/2 x to the negative half equals x e to the x over y squared times dy dx plus 1/2 y to the negative half times dy dx. Now everything on the right-hand side has a dy dx in it. We can factor out that dy over dx. the left-hand side, leave alone for the moment. And now I divide to get dy dx by itself. Okay, and before I've said I don't really like things like fractions within a fraction, but I think that if you try to simplify this any further, you're more likely to make a mistake than not, so we'll just stop there. Problem 18. Find the equation of the tangent line to this crazy-looking graph at the point 3, 1. So, to find the equation of a tangent line, I need a point and a slope, and I have a point, so we need a slope. So let's go ahead and differentiate both sides. I'm going to use implicit differentiation because I don't think I can solve for y here. So using implicit differentiation, I have an inside function. I'm going to use the chain rule. The 2 comes down. So we have 4 inside function, lower the power by 1. So it's the 1 times the derivative of the inside function. On the right-hand side, the 25 hangs out. The derivative of x squared is 2x. The derivative of y squared is 2y times dy dx. Okay, let's finish off our differentiation. The derivative of x squared is 2x. The derivative of y squared is 2y times dy dx. Okay, and now plug in x is 3, y is 1, and when we plug in, I won't have a derivative function anymore. I will have plugged into the derivative and just get a slope m. So 4 times 3 squared plus 1 squared times 2 times 3 plus 2 times 1 times m equals 25 times 2 times 3 minus 2 times 1 times m. Okay. 3 squared is 9, 1 squared is 1, is 10. So I have 4 times 10 times, in parentheses, I have 6 plus 2m equals 25 times 6 minus 2m. We'll do a little distributing. 4 times 10 is 40, times 6 is 240. 40 times 2m is 80m. Distribute here. 25 times 6 is 150. 25 times negative 2 is minus 50. Okay, let's get all the m's on one side. So if I add 50m to both sides, we'll have 130m. If I subtract 240 from both sides, I'll have a negative 90. And then we divide. So I get negative 90 over 130. It's negative 9/13. So that's the slope. So then the equation of the line, y minus y1 equals m times x minus x1. So y minus 1 equals negative 9/13. I'm sorry. Yeah. Negative 9/13 x minus 3. Okay. So y is just 1 minus 9/13 times x minus 3. Okay. That's a perfectly good equation. Problem 19. If this was not a definite integral, this would be a very challenging problem. But what I'm looking at is an integral from 1 to 1. And I know from my properties of integrals, the integral from a to a f of x dx is just 0, because we're not covering any distance. There's no width here. We're starting and ending at the same spot. So this integral is 0. Problem 20. Before I integrate, I need to get rid of the quotient because I don't have a quotient rule for integrals. So we're going to do some algebra first. I'm going to break this up into 3 separate fractions. I'm dividing each one by x separately. So we'll have x to the 4th over x plus negative 3x over x plus pi squared x over x that I'm integrating dx. And so this is going to give me an x cubed minus 3 plus pi squared. And now when I integrate, my variable is x. I'm going to use the power rule. So I'm going to get x to the 4th over 4 minus 3x plus pi squared x plus c. Pi squared is a constant, just like the negative 3. All right, next, evaluate this definite integral. This one we are going to have to figure out. And I have a quotient. That's no good, so I need to get rid of it somehow. I have this inside function, 5 plus x. Got to take care of that somehow. So we're going to use the u substitution. Let's let u equal 5 plus x. That's the inside of the square root. So then du dx is 1. So du equals dx. Okay. So I can rewrite this thing where I have a square root of u in the denominator. The dx is going to become a du, but I still have this x to worry about. Okay, so let's go back here and solve for x. So u minus 5 equals x. So I can replace this x with a u minus 5. Since I'm switching everything over from x's to u's, these are x values that I start with. Let's switch them over to u values also. So when x is equal to negative 1, u is equal to 5 plus negative 1, or 4. When x is equal to 4, u is equal to 5 plus 4, or 9. Okay. So when I switch from x's over to u's, I can change my limits of integration, and then I never have to go back to x's. All right, we still have a quotient, though, so let's do the same thing here that we did in the previous problem where we divided to get different fractions. So I'll write this as u. I'm going to write the square root of u as a u to the half. Okay, so we have the integral from 4 to 9. U over u to the half is just a u to the half power, and minus 5u to the negative half power. And I'm integrating du. So now when we integrate, I'm going to use the power rule, add 1 to the power, divide by the new power. Dividing by 3/2 is the same as multiplying by 2/3. If I add 1 to the power here, I'll have u to the positive half. Dividing by a half is the same as multiplying by 2. Okay. And these are u values, so I can just plug in here. I don't have to go back to x's. So we have 2/3 times 9 to the 3/2 minus 10 times 9 to the 1/2. And then minus the same formula except with 4 plugged in. So 2/3 times 4 to the 3/2 minus 10 times 4 to the 1/2. Okay. And you can leave it like that if you want to simplify away. Square root of 9 is 3, cubed is 27, divided by 3 is 9, times 2 is 18. Square root of 9 is 3, times negative 10 is minus 30. Okay, 4, square root is 2, cubed is 8, times 2 is 16, so we have 16/3. Square root of 4 is 2, times negative 10 is minus 20. Okay. And then, at some point we can stop simplifying numbers, right? So here I have negative 12 minus 16 thirds plus 20, which gives me 8 minus 16 thirds, which is 24 thirds, minus 16 thirds, which gives me 8 thirds. Okay. All right, problem 22. Evaluate the integral of sine x times cosine cubed x dx. What I'm going to do to begin with is to write out this cosine cubed as cosine x, which is then cubed, because then it seems very clear that I have an inside and an outside function. Since I'm integrating, I want to let u equal the inside function. So let's let u equal cosine x. Okay, so then du dx is negative sine x. So negative du is sine x dx. And I have that sine x dx in my original problem. So that's going to become a negative du. Cosine x is a u, so we have a u cubed. So I'm integrating negative u cubed du. Use the power rule. I add 1 to the power, divide by the new power. And now we go back to x's. So we have negative cosine x to the 4th divided by 4 plus c. Okay. Problem 23, again we have a integral. I have this inside function here. ln of x plus 1 is inside the squared function. So let's let u equal ln of x plus 1 and hope that something good happens. So when I differentiate, the derivative of ln of x is 1 over x, the derivative of 1 is 0. So du is 1 over x dx. And I kind of have that, right? If I rewrite this x that I have in the denominator, right, kind of off to the side, just rearranging, right? So there's nothing special about the order of multiplication. X times stuff is the same as stuff times x. Okay, so this 1 over x dx is going to become my du. So I have 4 over u squared du, which is 4u to the negative 2 du. And now I'm ready to integrate. So we use the power rule. I add 1 to the power, divide by that new power. So I have negative 4 over u plus c. U is ln of x plus 1. So we get negative 4 over ln of x plus 1 plus c, and that is our problem 24. We're going to use the fundamental theorem of calculus part 1. On this first problem, I'm taking the derivative of an integral. It's not a function, it's not just an x on top, it's a function of x. So we're going to use the chain rule here. Okay, where x squared plus 1 is the inside. So I know that the fundamental theorem says when you take the derivative of the integral, they wipe each other out, and you get the inside function, but as a function of x. The chain rule says don't plug in x, plug in the inside function. So I'm going to get sine of the inside function, x squared plus 1. The chain rule says then multiply by the derivative of the inside function. And the derivative of x squared plus 1 is 2x. So we have sine of x squared plus 1 times 2x. Okay. The next one, I have kind of the right idea, but the x is on the wrong spot. The fundamental theorem says that you have to have an integral from a to x, and I have from x to pi over 2. So what we're going to do is we're going to say, okay, I can flip my limits of integration. by having a negative come out. Okay, and now we have the derivative with respect to x of an integral from a to x of f of t dt. The fundamental theorem of calculus says the derivative and integral wipe each other out, and we get that inside function as a function of x. Okay, part C is a little bit more complicated because we're going from x squared to x cubed. There's no constant in here, so we're going to have to toss one in. So we're going to take an integral from x squared to 42, because that's the answer to life, the universe, and everything, plus the integral from 42 to x cubed. Okay. And now what I'm going to do is two things. The derivative of a sum is the sum of the derivatives, okay? And also for this first one, I'm going to flip my limits of integration. So we're going to have negative derivative from 42 to x squared, right, of ln of t squared plus 1 dt, plus the derivative with respect to x of the integral from 42 to x cubed of ln of t squared plus 1 dt. All right, and now this is going to be just like part A. I'm going to use the chain rule. My negatives on the outside. The derivative and integral will wipe each other out, but x squared is the inside function. So instead of replacing the t with an x, I replace it with x squared. So I have x squared squared, or x to the fourth, times the derivative of the inside function, which is 2x. Okay, same thing over here. And instead of replacing the t with an x, we replace it with x cubed, and then times the derivative of the inside function, 3x squared. Okay, problem 25. Sketch a graph that satisfies the following. So what I'm going to do is I'm going to put my axes down, and underneath I'm going to put down a number line where I'm going to list all of my relevant information. Okay, so stuff happens here at -3, and at -2, and at -1, and at +2, and at -4. Okay. So f prime is positive. That means that the function is increasing from -infinity to -3. So increasing until I get to -3. It's also increasing from -2 to -1. Okay. F prime is negative, so it's decreasing between -3 and -2. And then also from -1 on to infinity. F double prime is positive. That means that the original function is concave up from -infinity to -4, and also from 2 to infinity. F double prime is negative, so f is concave down from -4 to -2, and then also from -2 to +2. Okay, f has a vertical asymptote at -2. And a horizontal asymptote, y equals 0. And it has an intercept 0, 5. Okay, let's see if we can graph this thing now. One thing to keep in mind is that this intercept isn't on the edge of one of these intervals, it's in the middle. So when we graph this, we're not going to stop at this point. We're going to kind of just go through it. Okay, so maybe let's start with that one, right? So from -1 to 2, this is concave down and decreasing, so I have kind of a shape like this, and I want to go through this point, right? So we're going to start up somewhere higher and go through that point until we get down to 2. Okay. From 2 to infinity, it's concave up and decreasing, so I have a shape like this. So I want to continue on and keep decreasing, but we have to approach our asymptote. And that's a problem because we're already below the asymptote and going down. So I can't be getting closer to it. So we have to redraw. Say, okay, this first piece I have to be a little bit more gentle and not go below the axis, because for the second piece I have to approach my vertical asymptote. All right, moving on to the left, between -2 and -1, we have this concave down and increasing, so a shape like this, and I have to approach this vertical asymptote, so it's going to go down forever. Okay. To the left of that, it's concave down and decreasing, so we have a shape like this, and again I have to approach the asymptote. Okay. Between -4 and -3, it's concave down and increasing, so I have a shape like this. And between a -4 and infinity, it's concave up and increasing, so I have a shape like this. Once again, I'm not approaching this vertical asymptote, though, so I'm going to be like, okay, let's try this again. Maybe start on the left. Make sure that that horizontal asymptote works. So, okay. So we have our up shape approaching our horizontal asymptote. From -4 to -3, we get a shape like this. And then between -3 and -2, it turns downward and keeps going down forever. Okay, so you might have to redraw, or another way to do that is maybe to deal with the horizontal asymptotes first. I don't know, whatever your preference is. There you go.